So are there any questions on what I did last time or any previous time? Yes.
So this is about the statement that there are no types of particles in standard model such that they have the same quantum.
Yes.
The phi c.
Yes.
And the lepton turbulence have the same quantum numbers.
Okay. So the question is, why can't we map a Higgs to be, why can't we ask for the standard model Higgs to be a super partner of what? One of the electrons?
Yeah, one of the electrons.
Okay. So the argument is that they are doublets under SU2, they have the same hypercharge, they are neutral under SU3. And therefore we could imagine that these are super partners. Now the problem, I think, is that we need to have a coupling here. I think this is the problem. So this is a very good question. That this observation is that in fact there is a pair of particles in the standard model which have exactly the same quantum numbers. Okay. So that's a necessary but not sufficient condition for us to try and make them super partners. The problem, I believe, is that if we did put them in one superfield, then the type of coupling we would need to give the mass to the fermion, okay, we need that Higgs, so we would need the scalar part of a superfield to give a mass to the fermion of the same superfield. Okay. Now I wrote the cubic couplings last time which give masses to the fermions, and we saw that actually if you don't put a discrete symmetry which makes the Higgs superfield even and the lepton superfields odd, then there are many more couplings allowed. So here's one reason right away. Obviously you can't do that if the Higgs and the leptons are in the same superfield, because we would. Okay, so let me make that point a little more clear. But I think your question deserves a fuller answer, which I'll think about. But this actually brings me to where I wanted to start, which is that last time we saw that the superpotential in the supersymmetric part of the MSSM is mu h1 dot h2 minus a bunch of terms fij e li h1 ej bar minus fij t qi h1 ej bar minus fij u qi h2 ej bar. Okay, so these were the allowed couplings, and the couplings that we definitely don't want to have present, which are not present in this list and which we would like to forbid, are possible couplings like a lepton dotted with a Higgs, a lepton dotted with another lepton, singlet lepton, Li dotted with Qj and d bar k, and then even a term involving all the singlets, u bar I, all the Fock singlets, d bar j, d bar k, with some conditions. These we don't want to allow for phenomenological reasons, and the way to achieve this is to impose the symmetry under which all leptons Li, E bar I, and all quarks go to minus themselves, but the Higgs superfield go to plus themselves. The discrete symmetry, Z2 symmetry, and you can see that nicely allows all these terms and nicely forbids all these terms. Okay. Now your proposal would have been to identify H2, for example, with Li, with L1. H2, I think, or H1. Yeah, H1 probably is the H1 is the one with the charge of the conjugating. Sorry, H1 with L1, and we see that under this, of course, this symmetry is incompatible with that identification. But I think basically what your observation shows is that it's consistent with what I remember in the early days of supersymmetry, when people were trying out all these things and finding that one by one many of the nice things you might try to do with this symmetry don't work for some phenomenal activities. Okay. Now in today's lecture, I want to go into more depth.
Yes.
Yes.
So this association will allow one of the non-allowed terms to be present in this WMS.
Yes, you just wouldn't have been able to have this symmetry, right?
Yeah.
You can't simultaneously have H1 be even as well as odd. So you would have to fix one of those things, one of the properties for it. And it might, so probably the only thing you could do in that case is not have this symmetry, which is the same as saying that everybody is even. That's always allowed. Okay? Well, if you try anything else, then these terms may also not be allowed. For example, if I identified H1 with L and said both are odd, then this whole term would be odd. So this term would be not there, which means electrons would never get a mass. So that's the end of that requirement. On the other hand, if I said everything transforms as plus, then I could save the day, but then all these terms would come back. And if they are not forbidden by some symmetry, they'll certainly come back. If not at 3 levels, then with radiative corrections. Okay. Now I want to go into more detail about this symmetry. It turns out to be a very important symmetry called R parity. And so I'm going to make a little digression about R symmetry in n equals 1 supersymmetric theories. Now, the way I'm proceeding in this course, instead of starting out doing all the heavy formalism of supersymmetry, I'm doing it as and when required, and now is the time when our attention is getting focused on R symmetry and R parity. So this is the right time to discuss it. Now the idea is very simple. Since superspace contains complex coordinates, complex fermionic coordinates theta, it's natural to consider the symmetry operation theta A goes to e to the I alpha theta A independently on each component of theta, and clearly theta dagger A dot will go to e to the minus I alpha theta A dot. So this is a very reasonable thing to consider. It's very much like a rotation of a complex coordinate if you had a complex spatial coordinate. And on the other hand, since it doesn't affect the conventional part of space but only the super part, it will appear to us in ordinary field theory language like an internal symmetry. So this will be an example of something that's a space-time symmetry in superspace but an internal symmetry in ordinary space. Let me write that. How do we implement it? It's very simple. Consider a superfield phi of x theta dagger. Okay. So under this symmetry, we will say that this goes to phi prime of x theta prime theta dagger prime, which is equal to a phase e to the I alpha r phi. R phi is some number which is the charge under the symmetry of this chiral superfield, and then phi of x e to the now I always mess up my theta prime is this. What I want is that phi prime should be e to the I alpha r phi, phi of x e to the I alpha theta. I've got something wrong here, but I'll just fix it up. So Sorry?
The arguments of theta prime.
I think this is okay, actually. So as a function of theta prime, which is the so this goes to this. Okay, that's all we want. And now we can read off what the individual components of capital Phi do. So if capital Phi is equal to small phi plus root 2 theta psi plus theta theta f, then phi goes to e to the I alpha r phi phi. In other words, the scalar part has the R charge of the superfield itself. Okay. While the fermion, I might have written this wrong, but I think you can read off what I want. The fermion has one less unit and the auxiliary field has two less units. Okay. So this U1R symmetry is merely the statement that we make a phase transformation on phi and then another one on psi and f, which differ by 1 unit of this phase and 2 units respectively, so that we can ascribe the remaining to the transformation of theta. Okay, and now of course we must also transform d2 theta oppositely to theta. So this goes to e to the minus 2I alpha d2 theta. And with this assignment, integral d2 theta of w of phi will be invariant if the superpotential transforms by e to the plus 2I alpha. Okay, so it's up to us to find examples, but it's illuminating to see a few examples. In fact, even after knowing this thing for a long time, I guess I appreciated it better by looking at very simple examples. So let's look at simple examples. First of all, with one chiral superfield, which is by no means general or exhaustive, because you can have many in general and they can all have different R charges. Okay. With one field, consider the interaction d2 theta phi square, which is just a mass term. Okay. So here, this will be invariant. Seeing this, if you assign phi an R charge of 1. Okay. What does it mean to assign phi an R charge of 1? It means phi, the scalar part goes to e to the I alpha phi. The fermion from this equation doesn't transform, and the auxiliary field transforms oppositely to phi. Okay. So we expect this to be an invariance of the terms in the action which arise from reducing this to ordinary space, which are phi star phi. So let's put an m here. Then this is m squared phi star phi plus m psi psi plus complex conjugate after eliminating f. First of all, note that f, eliminating f sets f star equals phi. Okay, that's compatible with this. Secondly, this is clearly invariant under a phase rotation of phi and no phase rotation on psi. Okay, there isn't in fact any phase rotation on psi which you can make when there is a mass term. This is well known, because that phase rotation is chiral symmetry. So if we have a mass term, there is no chiral symmetry, therefore there is no phase rotation on psi allowed. And that's great, because this particular example with these choices of R charge for the superfield just gives us a phase in this term and nothing in this term. So it's consistent and correct. It's a correct symmetry of the theory. It's also one of the rare examples where the symmetry is non-anomalous, because after all it doesn't act on the fermions, but most often it's anomalous. Okay. Let's look at a slightly more complicated example. Still with one field, but now we consider lambda integral d2 theta phi cubed. If we had one field, we can't put phi squared and phi cubed and hope to have R symmetry, because we have to give phi a definite R charge. So here we would like to give R phi as 2/3 in order for this whole thing to have a total R charge of plus 2 to cancel the change of the measure. Okay. Now the interaction turns out to be lambda phi star phi squared. Well, lambda squared probably. And another term is lambda phi psi plus complex conjugate. And this time the auxiliary field is set equal to phi squared. And in fact, if we see what happens under this, phi goes to 2/3 I alpha phi. Psi goes to this minus 1, so minus 1/3 I alpha psi, and f goes to minus 4/3 I alpha f. Now notice that this time f star goes like phi square, which is good because the equation of motion is f star equals phi square. Secondly, you see that on this term, of course, any phase rotation on phi will give this term invariant, but this one is invariant now if I give phi this phase and psi precisely this phase because they are two psi's. Okay, so it's nicely invariant. What we see is that R symmetry is a clever way of finding a class of symmetries in which bosons and fermions in the same superfield, therefore in the same supermultiplet, can transform differently. And we see that the underlying reason is this type of interactions governed by supersymmetry have these symmetries. Now the problem is, this looks very exciting, but the problem is that R symmetry is generically anomalous.
Once we have gauge fields.
Yes, which we will have. Okay, 1 minute. No, why do we need gauge fields? I'm thinking of it as a global symmetry. It's an anomalous global symmetry.
What's on the right hand side of the group? Then you take use what? Is there a gauge fields?
But the point is that if I have an anomalous global, well, that's the general question about any anomalous global symmetry. It doesn't render the theory inconsistent.
No, but the answer is that it's f star f of some present gauge field. So it's violated by instantons of that gauge field.
Okay.
In the absence of such instantonic configurations, the thing is symmetric. The symmetry is preserved.
Yeah, I'm just trying to figure out what supposing for some reason I make some world, hypothetical world based on only chiral multiplets with no vector multiplets. Okay, and therefore no gauge fields. Could I assume this to be a consistent symmetry of the quantum theory?
I think so.
I could assume it to be a consistent symmetry. That means the fact that, okay, I'm just a little puzzled about this, but you're probably right.
It's like if you see the chiral rotations,
Right.
then you can use f star f. In the absence of...
That's correct. That's correct. Thank you. Of course, we've seen that there are some trivial examples where it's not anomalous, such as this example, but that's hardly general. Now, instead of going into the details of when it's anomalous and when that becomes a problem, I'll notice the second problem of R symmetry, which is much simpler and which is more phenomenological, which is that vector multiplets are necessarily neutral. That is the R charge. I just told you what's the R charge of scalar multiplets or chiral multiplets is something we can choose. But for vector multiplets, they are real. Right? So a real multiplet cannot transform under a phase. So it's necessarily neutral. But this implies that the Gaugino transforms. Because remember, the Gaugino multiplies theta, theta, theta daggers. Then you get lambda daggers. Okay? So the net phase in theta, theta, theta dagger is 1 unit of phase, alpha, and therefore lambda probably plus, I think, opposite of what? Let's just see the term and we'll see it quickly. So, because V equals various terms that are trivial in Wessoino gauge, then theta sigma mu theta dagger A mu. So the fact that V doesn't transform, this piece doesn't transform under R symmetry because of equal theta and theta diagonal, so A mu doesn't transform. But at the next level, we get this plus the complex conjugate. Now all this stuff transforms. 2 plus alphas and 1 minus alpha, so a net plus alpha, so this transforms with e to the minus alpha, which means lambda transforms with e to the plus I alpha. It's not important whether it's plus or minus, but the important thing is this forbids Majorana masses like lambda for the gauginos. Now, of course, in the fundamental theory, we don't put any masses for the gauginos because the corresponding gauge fields are massless, in the Lagrangian at least, by gauge invariance. However, eventually supersymmetry is broken, and if R symmetry remains a symmetry, then we'll be forbidding mass terms for the gauginos in the broken supersymmetry theory, and that means that there will be predictions like having massless photonios coupling with electromagnetic strength or whatever, and that's flatly in contradiction with experiments. There just cannot be massless fermions just with the quantum numbers to be superpartners of the gauge fields, even if supersymmetry is broken or in any effective approximation to this theory. Okay. So that means that R symmetry as a U1 symmetry is not useful. However, the subgroup, we know that typically with anomalous symmetries there is a good subgroup which could be discrete, and in this case it's obvious just again by inspecting this Majorana mass term, lambda goes to minus lambda could be a good symmetry. This is a Z2 subgroup. And this one we'll name R parity. So it's the parity subgroup of U1 R. Okay. My claim is, first of all, this will be non-anomalous, and secondly that it's a very useful concept in the MSSM. So in order for it to be useful, we should now associate discrete R parity to every superfield in the MSSM. And so discrete R parity. And what this will say is that phi, a given superfield, can go to plus or minus phi under R parity simultaneously with theta going to minus theta, and theta dagger will be the same. Okay, and from here we can read off that if this goes to plus or minus phi, then the scalar part goes to plus or minus itself, but the fermion part goes to minus or plus itself, and the auxiliary part goes back to plus or minus itself. Okay? This always has the same transformation as the superfield. This has the opposite one because theta goes to minus theta. This has the same because this multiplies theta theta. So we see that basically we have a choice of assigning an opposite parity to the phi and psi of every chiral superfield. Okay, and now let's recall our terms that we started talking about and that we talked about yesterday. So mu h1 dot h2 minus fij h1 e1j, and then the quark couplings. Okay, these motivated us to give the transformation Li, E bar, J, etc., all the quarks to minus themselves, so they are all odd under R. The Higgs, on the contrary, are all go to plus, so they are even, and of course the vector multiplet is even. So we reinterpret that symmetry we saw before, which forbids some unwanted terms in the MSSM, as R parity. So R parity For example, what was it? QI, any of those? LIQJ, URK, I think it was K. Yes.
Is this also the entire non-anomalous subgroup of the
I suspect it is, yeah. I don't know for a fact, but I can't see. Normally it's broken into some Zn and there doesn't seem to be any natural N in this. Yeah. Okay.
But it is true that this is non-anomalous.
This is non-anomalous, yeah. And this plays a fundamental role in the MSSM for the following reason. First of all, it forbids the unwanted couplings. Okay. So we promote it to a fundamental requirement property, if you like, of MSSM, and therefore henceforth we will say that MSSM, the minimal supersymmetric standard model, conserves R parity. Anything we do to it, even including breaking supersymmetry, will preserve R parity. Now, this has a fantastic consequence. First of all, you could ask why. There is no rationale. I haven't given you any proof. But then, what is this MSSM for? After supersymmetry breaking and adding the Higgs mechanism back in, it will supposedly reproduce particle interactions at some energy. So, it's a phenomenological statement which could be wrong. However, what this does, R parity does, is to make it minimal. You can't argue with that. Because if you don't include it, then of course all these terms are there. Then you have to go through some other contortions to forbid or make them small. You can always get away in phenomenology without making it zero if it's small enough. Okay, but then there are some other contortions. This is the simplest way to ban a whole class of terms. Okay, but it has a very, very beautiful phenomenological consequence which I want to show you now. Let's take it apart and see how it operates on individual particles. Okay, so we've seen that lepton superfields. So let's take an example of a lepton superfield. Let's take the electron part of the left-handed lepton doublet. So this has as its first term the selectron, as its second term the electron. Okay, now we've just seen that the R parity of the superfield is minus. That means it's minus for the selectron and plus for the electron. Okay. Now do the same exercise with the neutrino and with all the quarks. It's exactly the same because all of them are odd under R. So it's always minus for this quark and this neutrino and plus for the quark and the neutrino.
So all standard model.
So all standard model. Well, so far we're seeing that at least in the sector of these standard model fermions, it's the standard model fermion which is plus and the unyet discovered fermion which is R odd. Okay, but this goes further with the Higgs. You see, with the Higgs we assign an opposite R parity, and the Higgs superfield starts with the Higgs field. Okay, and then its next term is the Higgsino, for which I probably don't have any notation. Let's call it psi. Okay, but now because the superfield has a positive R parity, this guy is plus and this guy is minus. Okay, but this guy is the Higgs and this guy is the Higgsino. And finally, to complete the argument, of course, you've already seen, we started with this observation with the vector multiplet. Because the whole multiplet is R neutral, A mu goes to A mu, where A mu can be any of the photon or can be the BNO, VNO, and the B, the W, and the gluon, while the corresponding gauginos go to minus. So precisely this convenient assignment of parities makes all known or standard model particles are even, all superpartners are odd. Well, superpartner is a double-edged word. If something is a superpartner of something else, then that thing is a superpartner of this. But now we are using it in the language where the superpartner is the unknown, undiscovered superpartner, while the particle is the known standard model particle. Okay? And so in some sense, it at least gives us one label to hang on all the particles which we haven't found. They are all R odd. Okay? And in particular, this implies a very dramatic consequence. It's instantly, we are used to these things, superpartners have to be produced in pairs. And it's quite amazing. We are really not phenomenologists, and we haven't done any serious phenomenology. But a little bit of pulling around with this, and we've come up with a very dramatic experimental prediction, which is that superpartners must be produced in pairs, because whatever you start with are standard model particles. They are even, so the entire input of your experiment, whether it's a hadron collider or electron collider, is all R even. Whatever goes out must, if it has any superpartner, must have an even number of them. And that creates a threshold for production of superpartners, which is double what it would be, at least double the energy of the lightest one. And there's another consequence. The lightest among the superpartners, this is all, by the way, after supersymmetry breaking. Okay, because we haven't used much information, but just that R parity remains the symmetry of the theory even after supersymmetry is broken, even though we don't yet know how it will be broken, just as long as we believe that. Then the lightest supersymmetric partner must be stable, because it's the reverse of the above statement. It's an R odd state. There is no lighter R odd state since it's the lightest one, and therefore it must be stable. In fact, it's reminiscent. It's not due to, well, it's indirectly due to supersymmetry, but it's reminiscent of a BPS kind of statement that something is stable just because it's the lightest object in its class. But we shouldn't get too carried away. There are other statements like that already in particle physics. But anyway, it's a lovely fact because it gives us something to look forward to, and of course this ties into things about dark matter candidates and so on, because we're looking for something stable that's hanging around the universe, and this just looks so nice. Okay, so I did this digression on R parity. We could have let it go by saying that there was a discrete symmetry, but I think this has given us a little bit more illumination of what this symmetry is for. And it will be kind of a rule that whenever we allow for R parity violation, then it will not be the minimal supersymmetric standard model, it will be some non-minimal thing, which, as I said, is not at all ruled out by experiment. Okay. A last observation, one may wonder why R parity miraculously turned out to be a symmetry of the parts of the Lagrangian which we want, and the answer to that is that you can identify it in the MSSM. This is an exercise. Show that in the MSSM, the R parity of any particle is the same as -1 to the 3b plus L plus 2s, where B is baryon number, L is electron number, and S is spin. Okay, and since the MSSM, like the standard model, conserves baryon and lepton number, and although it doesn't conserve spin, of course it conserves fermion number, the spin modulo 2, that's enough to say that with this kind of number assigned to every particle, the thing has to be invariant, which also shows that the interactions I wrote which weren't in the desired class were violating of one of these B or L. Good. Okay. So are there any questions on this? Is there a question for me?
Sorry, just say what baryon number and what lepton number.
Baryon number is 1/3 for quarks and minus 1/3 for antiquarks. Lepton number is 1 for leptons and minus 1 for antiquarks.
And leptons is to the electron and neutron.
Yes. And 0 for the Higgs. Therefore, you can see any of your favorite Higgs, and 0 for the gauge field, so you can work it out, and therefore also for the super partners thereof. In fact, this 2s really gives it away, because after all 2s is 1 between a fermion and a boson. So within the same supermultiplet, it will be minus for the fermion whatever it was for the boson, which makes it R-symmetry within a given multiplet, because these will be the same within that one. So you just need to check a few cases and you're through. Okay. So now I turn to the next important topic, which again I could have discussed earlier as part of some formalism of supersymmetry kind of course, but I'm doing it now for the following reason. I've already written down for you an MSSM, and it should be evident to all of you that this model as it stands is complete nonsense. Okay, it's an extension of the standard model by making all fields into superfields, making Higgs doublet into 2 Higgs superfield doublets. That's about all we did. And it's complete nonsense because it predicts an enormous number of particles, including their masses, which are fixed to be the same as the masses of the particles whose partners they are, and they are not detected in experiment. So this model is not consistent with experiment. So supersymmetry must be broken if it's there at all in the first place. Now, thinking of it that way, we realize the need to do something to this model to incorporate SUSY breaking, but there are many different things which we could imagine doing. The first of which would come to our mind, having studied the standard model, is to say that supersymmetry must be broken spontaneously. So we would like to study supersymmetry breaking spontaneously. Okay, but this itself has 2 branches. One is classical, and the other goes by the name of dynamical or quantum. The idea here is that classical spontaneous supersymmetry breaking means we take the classical Lagrangian, and somehow when we minimize it, we find that in that minimum supersymmetry is broken. Okay. Dynamical is when such a thing doesn't happen in the classical Lagrangian, but it does happen in the full quantum corrected Lagrangian. Okay, where you imagine adding in quantum corrections in whatever way you know how. You could add in the perturbative ones, some non-perturbative ones due to instantons. You could guess what are the corrections using some symmetries of the theory. Whatever you do, it would be something that would occur after quantum corrections are turned on. Okay, it would have different signatures, but would achieve the same goal, of course, of breaking it spontaneously. But supposing neither of these works out, then you could break it explicitly by adding some terms in the Lagrangian which are not supersymmetric. Now this is very unpleasant to contemplate, but it's actually what we are going to do eventually. And the reason is that what looks explicit in the MSSM could be dynamical or spontaneous or any other, or one of those things in the underlying high energy theory that it comes from. And since we are working at the level of present day energy phenomenological Lagrangian, we shouldn't expect every breaking effect to be spontaneous in that Lagrangian. In fact, there's one stronger reason, at least for me, which is that ultimately we know that this theory ought to be coupled to gravity at some high scale, and we know that supersymmetry has a nice extension as supergravity, which makes it local. Okay, so you would think that if supersymmetry wants to be broken via Higgs mechanism, Higgs-like mechanism, then of course first we need to make it local by introducing gravity and then breaking it using gravity. So that's always a possibility, and it doesn't contradict the fact that in the MSSM it appears as an explicit breaking. Okay, so explicit breaking should always be thought of as due to some unknown mechanism in the underlying theory, and these mechanisms are not so unknown. We'll be discussing them later on. but they manifest in some underlying version of this theory or some higher energy version of this theory. And then it might be spontaneous and it might be related, for example, to supergravity. Okay. So we should be prepared to have to do this, but we shouldn't do this until we have ruled out that we can do this, which is what we'll do today and in the next lecture. Yes.
Sorry, it's slightly out of the context of the course, but do you learn very much about the possible nature of an underlying theory could be from a form of explicitness?
Yeah,
I mean, does the form of the explicit supersymmetry breaking constrain the underlying?
I think it will, yes. I'm still in the process of understanding this myself, so I can't give a more detailed answer, but when we come to this issue, when we actually grapple with the explicit soft SUSY breaking terms, then we'll ask this question.
So we also have to break gate symmetry.
Yes.
And the potential that does that, will that importantly involve supersymmetry breaking or not?
Yeah. So again, I'll put off discussion of all such things because I'm actually the way I'm doing this is I'm sort of trying to get the big picture myself, which I don't have. But my guess is that since supersymmetry is certainly broken at a higher scale, even if slightly higher than electroweak, one should probably first break supersymmetry and then talk about a Higgs mechanism, which I think is also the order in which DGR approaches it. Okay. Now, again, there are many useful theorems connected with supersymmetry breaking, and we'll prove one or two later. But I'm going to persistently take this new final phenomenological approach that I'm enjoying so much in this course. And so I'm going to ask so SSB usually means spontaneous symmetry breaking, but in this course it will mean spontaneous supersymmetry breaking with chiral multiplets. So we are going to first discuss a pattern, possible pattern of such supersymmetry breaking with chiral multiplets only, and then we'll introduce vector multiplets. Now we already saw that with chiral multiplets, so from now on for some time we assume that we have a bunch of phi I, where I is some unknown index ranging over any